Dear students, I am Deepak Videv, Assistant Professor, Department of Electrical and Electronics Engineering with the Academy of Science and Technology. Our today's topic is Poyinting theorem, and these are the topics to be covered under Poyinting theorem. So I will first explain about Poyinting vector and Poyinting theorem, and in the subsequent videos I will be explaining about power flow in coaxial cable and also about complex average Poyinting vector. The power flow in coaxial cable is an example for, or it's an application for Poyinting vector and Poyinting theorem. Okay, before directly entering into Poyinting theorem, let us first try to understand the wave propagation. In the figure, an electromagnetic wave that is propagating in a particular direction is shown, and it is evident that the electric field component and magnetic field are mutually perpendicular to each other, and for both electric field and magnetic field the variation in its magnitude take place only in the direction of propagation. In this electromagnetic wave, when it travels from one end to another, it also carries some amount of power within that electromagnetic wave. We have to determine that power. That is the importance of Poyinting theorem. We know that for electric field, its unit is volt per meter, and the unit of magnetic field is ampere per meter. So if we just multiply these two terms, we will get another term, and its unit will be, in the numerator we have voltage and ampere, so volt into ampere will give the dimension of power, that is watt. In the denominator there are 2 meters, so it will be meter square, so watt per meter square. So if you multiply electric field and magnetic field, we will get another quantity, and its dimension will be watt per meter square or power per meter square. So it indicates that it is a power density. From this observation, we may directly enter into Poyinting theorem, and it is a statement of conservation of energy for electromagnetic field. This theorem states that the vector product of electric field and magnetic field at any point is a measure of the rate of energy flow per unit area at that point, and the direction of power flow is perpendicular to both electric and magnetic field. That is, if you take the vector product E cross H, we will get the energy flow per unit area. Energy flow means it is the power per unit area, and its direction will be perpendicular to both electric and magnetic field. So if you take the vector product, you will get another vector whose dimension or whose magnitude directly gives the power density at that point, and its direction will be perpendicular to both electric field and magnetic field. That is why we are taking the vector product, and this resultant vector, that is the vector product of electric field and magnetic field, is denoted by the letter S. In some textbook it may be represented by P, so here I am represented by the letter S. This vector is known as Poyinting vector, and it gives the power density at a particular point, and it is directed perpendicular to both electric and magnetic field. So from this discussion we can conclude that the power will be flowing in a direction perpendicular to both electric and magnetic field in an electromagnetic wave. So this statement of Poyinting theorem is a very simple statement, but we have to derive the mathematical statement of Poyinting theorem. So this derivation also starts from our Maxwell's equation. So equation 92 represents one of the Maxwell's equation that's directly coming from the Ampere's circuital law. If you take scalar product with electric field on the both sides of equation 92, we will get the equation 93. That is, we are taking dot product with electric field E on equation 92 and it gives the equation 93. In equation 93, we are using a vector identity. That is, we have the vector identity del dot E cross H. For any vector E and H, this vector identity is applicable. So from equation 94, we can substitute for E dot del cross H. That is, here there is E dot del cross H is here. So other terms are taken into other side. So we will get this term in the left side. So we are just substituting for this term using our vector identity that is described by the equation 94. So we will get the equation 95. So from equation 93, using the vector identity in the 94, we will get the equation 95. So you have to remember this vector identity that is shown by equation 94. Next, in the equation 95, we have to substitute for del cross C. For that, we can use another Maxwell's equation, that is del cross E is equal to minus dou B by dou T. So in equation 95, we will substitute for del cross E as minus dou B by dou T and we will obtain this equation. So here we substituted this one. Okay, so we obtaining this equation, and after rearranging, the equation become this term. Here the J dot E is this one and this becomes this term because D is equal to epsilon 0 epsilon r into E. So if we substitute D as epsilon into E, the equation, this term becomes this one. And here also for B, we can substitute mu 0 mu r h, that is mu into h. So this term becomes mu into dou mu into h into dou h by dou t. That is this term. Okay, so this term is taken into this side and this equation becomes this one. We will be substituting for D as epsilon into E, and for B we can substitute as mu into h. So that's why we are obtaining this equation. Okay, next we can use the relations of energy density. That is, we studied about energy density in electric field and derived the energy density as half into D dot E. So we can use that relation. So here this term, that is this term, there is E dot dou E by dou T. It becomes half into dou by dou T of epsilon E square, where epsilon E square is nothing but the energy density, that is half into D dot E. Similarly, we can write in the magnetic field similar expression. Here there is D dot E, so instead of D in magnetic field it becomes B, instead of electric field it becomes H. So this term represents the energy density in electric field, and this term represents the energy density in magnetic field. So energy density in electric field is given by half into d dot E. Similarly, energy density in magnetic field is given by half into B dot H. That's why we are obtaining this equation. So this is the important equation in Poyinting theorem. Now let us take volume integral in the left side and right side of the previous equation, and we will get this big equation. In this equation there is del dot E cross H. So here we are taking divergence. So this divergence can be eliminated by using divergence theorem. So by using divergence theorem, this volume integral can be converted into surface integral. So it becomes integral over the surface E cross H ds. The divergence part is, this divergence part is taken out of that integral, and it becomes surface integral over the surface E cross H ds, and all the remaining terms are same. So this 100th equation, this equation is the mathematical form of Poyinting theorem. Now let us try to evaluate the physical meaning of the equation 100. If you consider the terms in the right side of this equation, you can find that each of the terms represents the power associated with different quantities in a particular region. So let us first consider the first term, this term. Here in the integral, inside the integral, there is a product, that is vector j dot E. Vector j is the current density and vector E is the electric field. For current density, its unit is ampere per meter square, and for electric field, its unit is volt per meter. If we multiply these two terms, the resulting quantity will have a unit of watt per meter cube, that is power density, and we are multiplying that quantity with volume dV. So the resulting quantity, if we multiply J into E and dV, the resulting quantity will have the unit of watts. So this first integral represents the power, but in that term there is current, density and electric field. So this power is associated with conduction current and electric field. So we can conclude that it is the power that is dissipated in resistance. We know that in resistance the power loss will be there only when a current flows through it. So this first term represents the power that is associated with resistance or power loss in the resistance in a volume. Similarly, we can evaluate the next term. In that term, there is a partial derivative, and we are multiplying electric flux density and electric field and volume. If you evaluate dimensionally each of these terms, you can find that it is also representing a power, but it is the power associated with the electric field. In this equation, there is no terms associated with conduction current, so we can surely say that it is not the power associated with the resistance. So it is the power or energy associated with electric field that are stored in capacitive element. Thus, the second term represents the energy stored in the capacitor in a region. Similarly, we can evaluate the third term also. It also represents the energy stored in a magnetic field, and we can say that in inductor the energy is stored in magnetic field. So the third term, that is this third term, also represents the power associated with another element in electric circuit, that is magnetic field. So in this equation, The right side represents the energies that are stored or dissipated in various elements in a region. This can be represented by this figure. Here you can see that this term is, that is integral over the volume J dot E dV, is the power or energy associated with the resistance, and the next term, that is integral over the volume dou by dou T of half into D dot E dV, represents the energy stored in capacitor, and the third term, integral over the volume dou by dou T half B dot H dV, represents the energy stored in magnetic field. Thus, the previous equation is just represented pictorially in this figure. So, each of the terms in this, in the right side of this equation, represents the power in different elements in a region, and they are the power flowing into that region, into that volume. So, here also, this term also represents the total power flowing into that volume. So if you want to find the total power flowing out of a volume, you have to take negative of this integral. So if you take surface integral of E cross H ds, it becomes the total power flowing out of the volume. That is shown here. The total power flowing out of the volume will be integral over the surface. Surface integral is double integral. That's why here it is shown as double integral. So surface double integral E cross H ds represents the total power flowing out of the volume. So let us try to conclude this session. Again, if you consider the equation 100, the sum of the expressions on the right of that equation must therefore be the total power flowing into the volume. So the total power flowing out of the considered volume will be integral over the surface E cross H ds. Here E cross H is the Poyinting vector, and its dimension is power per meter square. So it also represents the power density at any point. Now let me conclude this session. In today's video, we studied about Poyinting vector and Poyinting theorem. We derived the mathematical form of Poyinting theorem, and its physical meaning is also explained. I hope all of you understood these topics, and thank you.